Hello everyone and welcome to my channel Tuner on Security. In this video I'm going to show you how to solve a forensics CTF challenge from Crate-CTF 2023. The challenge is called Unicorn Shredder. I've summarized the most important information about the challenge here. As already mentioned, the challenge is within the forensics area. The task description reads: we requested a trial version from the company that claimed to make a shredder approved for use on top secret images. Why just delete images when you can shred them? You'll find a link to the challenge in the video description below. Let's jump into the challenge. Here we have the challenge. It's called Unicorn Shredder. We requested a trial version from the company that claimed to make a shredder approved for use on top secret images. Why just delete pictures when you can shred them? Let's open this link. Unicorn Shredder, military grade, drag and drop image to shred. And here below we have inspect the shred bucket here. So let's click the shred bucket. So we seem to have a lot of files here. And this bottom file seems to be a possible candidate to be a flag. So let's save this image. And we see we have a lot of other files as well. But hopefully we don't need to check everyone. We're hoping that the first file we found was the one with the flag. So let's go back. I've now opened the file that I think contains the flag in MT Paint. So let's analyze this image a bit. I'm going to zoom in and then I'm going to check each block here. So we seem to have blocks of 30 by 30 pixels. Yeah, that looks right. And the size of the whole image is 900 by 600 pixels. So the next step now is that I want to create a test image of the same dimensions and 900 by 600 pixels, which contains blocks of 30 by 30 pixels, where each block has a unique color code. And then I will try to run it through the shredder and see what happens. Now I've created a Python script to generate a PNG test image with the blocks with unique colors. So I'm going to walk through this Python script here. So first, a summary of what the program does. The program generates a PNG image file of the size 900 by 600 pixels, since that was the size that we saw that our shredded image has. The image is made up of 30 by 30 pixel blocks. Each block has a unique color, RGB. The colors are generated by incrementing a counter and converting it to an RGB color. The generated image will be used by the shredder to generate all possible combinations of shredded images. We can then use the original image and the shredded images to reverse the shredding of the lost image. I import an image from PIL, and this helps us to work with PNG images. Let's move down to the main part of the program. So here I've just hard-coded the width of the image to 900 pixels and the height to 600. And I've also defined the block size to 30 pixels. Then I call the function generateImage, passing along these arguments here. And finally, I save this image. So let's go through the generateImage function. We start by creating a new image with the width and height specified. Then we have the number of X blocks, which we get by dividing the width with the block size. And we do the same for the Y blocks, where we divide the height by the block size. Then we initialize our color counter to 0. Then we have a for loop, and this loop iterates over each row of blocks in the image. So it's a nested loop, as you see here. So we also iterate over each column of blocks in the image. So together these two nested loops go through each block in the image. So we need to convert this color counter to an RGB code so that we get a unique color code for each block. And the RGB color model represents colors as a combination of red, green, and blue, with each component ranging from 0 to 255. And here you see that the double slash operator performs integer division, and then the percentage operator calculates the remainder. So we calculate red, green, and blue. We get an iteration where we start by 0, 0, 0, then we go to 0, 0, 1, 0, 0, 2, all the way up to 0, 0, 255. Then we increase the G, the green, and go to 0, 1, 0, 0, 1, 1, 0, 1, 2, all the way up to 0, 1, 255. Then we increase that one again, and so on. We now create a tuple representing the RGB color. We now calculate the coordinates of the current block in the image. So the block size is the size of each block in pixels. So we take X times block size as well as Y times block size. So that's the starting pixel. And then we add 1 to X and Y. So we effectively add 30 pixels in each dimension. Then we fill the current block with the generated color. So the paste method of a PIL image object fills a specified region with a specified color. So image paste color and then the block. And finally, we increment the counter. So the next iteration, a new color will be generated. So we loop through all the blocks here, and then we return the image. So let's try this script out. Python generate PNG with blocks unique colors. And here I have opened the resulting file. So as you can see, we go from black to a bluish color, and then we continue like this, just to show you that there are unique colors, since it's not all that easy to see with the eye. We start here. So it's just 0, 0, 0, red, green, blue. And then if we go to the next block, you see that blue has 1. And then we go all the way up here, where blue is 255. And then we continue, just like I described when we went through the code. Okay, so each block here has a unique color. That's all we need to know here. Okay, so let's upload the test file that I've created. And then shred it. And then we'll save this one. And let's continue shredding. And I'll keep doing this 20 times or something like that, so that we get a sample to test our Python program with. Now I've saved a lot of shredded images, so let's have a look at them. We can sort them by size. So as we see, we have a lot of image files of the same size, and probably a lot of them are duplicates. So what I've done now is that I've created a script to find the unique images. So let's go through that Python script. Here's the script. The script copied non-duplicate files from a source directory to a destination directory based on their SHA-256 checksums. So I don't think the size of the file is enough to determine if it's unique or not. So I decided to use the SHA-256 checksum. First we have some imports, hashlib, and some shell utilities. So let's start with the main part of the script. Here I just set the source directory, which is shredded, where all the shredded images that I generated from my test image are located. And then we have a destination directory where we put the unique images. Then we just call this function copy non-duplicates. So let's go through that one. This function copies non-duplicate files from the source directory to the destination directory. And we take source and destination directory as parameters. We create the destination directory if it doesn't already exist. If it does, that's also okay. We initialize an empty dictionary that will be used to store the checksums of the files. We iterate over each file in the source directory. We just construct the full path to the current file. We check if the current path is a file as opposed to a directory. Then we calculate the checksum of the current file. We check if the checksum is not already in the file checksums dictionary, the one we initialized up here, which means the file is not a duplicate. So if the checksum is not already in the dictionary, we know we've found a new unique file. We add the checksum of the current file to the file checksums dictionary. We construct a full path to the destination file. Then we copy the current file to the destination directory. We also print to the screen that we are copying this file. And if it's a duplicate, we print that we skip this duplicate file. Okay, so let's have a look at the calculate checksum function as well, the one that we call down here. This function calculates the SHA-256 checksum of a file, and this algorithm generates a unique hash value for each unique input, so it can be used to check if two files are identical. We create a new SHA-256 hash object. We open the file in binary mode for reading, and then we read the file in chunks of 4096 bytes until there's nothing left to read. We update the SHA-256 hash object with the current chunk of data. And finally, we return the hexadecimal digest of the hash object, which is the checksum of the file. So that's pretty much it for this script. Let's try and run it. Okay, so here we see that in the beginning we copy a lot of the files since they are unique, and then we get more and more duplicate files. Let's go into the unique directory and have a look. Okay, so these are our unique shredded files So we'll assume that we have found all different possible shredding algorithms. So now for the third and final Python script that I created to solve the challenge. The purpose of this script is to decipher the shredded image, or to reverse the shredded image. So here at the top I just summarized where we are at. So let's go through that. So an image was accidentally shredded, or not really accidentally, but it's lost, and this Python script will help to recover it. We have access to the shredder. The shredder shreds images by randomly shuffling 30 by 30 pixel blocks. We generated a new image, original.png, of the same size as the shredded one. We then shredded the new image and found out that there are 11 different ways to shred and places the 30 by 30 pixel blocks. The new image is made up of blocks of 30 by 30 pixels, and each block has a unique RGB code. Thus, we can uniquely identify each block by checking what the color code is. All the shredded images are available in the directory shredded. The script applies the different mappings in reverse to lost.png. The different results from the reversing are stored in a separate folder, reversed, with the names reversed1.png, reversed2.png, etc. We have some imports. And let's start in the main function, or in the main part of the program. Here we have some definitions to start with. The size of the blocks in the image is 30 by 30 pixels. That's the block size. We have the path to the original image. Then we have the directory where the shredded images of the original are stored. We have the path to the lost image, which hopefully contains our flag. That's lost.png. We have a directory where the reversed images will be saved. We create a directory where the reversed images will be saved if it doesn't already exist. We initialize an empty dictionary that will be used to store the mappings from the original image to each shredded image. We iterate over each file in the shredded image directory. We construct a full path to the current shredded image file. Then we find a mapping from the original image to the current shredded image. So that's our mapping. We add the mapping to the all mappings dictionary with the shredded image file name as the key. We iterate over each item in the all mappings dictionary. The enumerate function is used to get the index of each item. We construct a full path to the reversed image file. And we apply the mapping to the lost image and save the resulting image to the reversed image path. Okay, so let's go through the functions that we call. We can start by looking at the find mapping function. This function takes two image file paths and a block size as input and returns a mapping from the blocks in the original image to the blocks in the shredded image based on their colors. We get a list of the colors of the upper leftmost pixel of each block in the image for the original image. And we get a list of the colors of the upper leftmost pixel of each block in the image for the shredded image. We initialize an empty dictionary that will be used to store the mappings from the blocks in the original image to the blocks in the shredded image. We iterate over each color in original image colors, and the enumerate function returns both the index I and the color at that index. We find the index of the first occurrence of that color in shredded image colors. We add an entry to the mapping dictionary where the key is the index in original image colors, and the value is the index in shredded image colors. And finally, we return the mapping. So let's have a look at the get block colors function, since we call that one from file mapping. This function divides an image into blocks of a specified size and returns a list of the colors of the upper leftmost pixel of each block. We open the image file at the given path using the PIL library and assign it to the variable image. We get the size of the image in pixels and assign the width and height to the corresponding variables. We calculate the number of blocks in the X horizontal direction of the image, and we do the same for the Y, the vertical direction. We initialize an empty list that will be used to store the colors of the upper leftmost pixel of each block. We have a nested for loop, which iterates over each block in the image, so Y and X. We calculate the coordinates of the current block in the image. We crop the current block from the image by using the PIL image object and the crop method. We take the color of the upper leftmost pixel as the block color and append it to the block colors list. And then we return this block colors list. Then we have our final function, apply mapping. This function takes an image file path, a mapping, a block size, and an output path as input. It applies the mapping to rearrange the blocks in the image and saves the resulting image to the output path. It opens the image file at a given path using the Python image library and assign it to the variable image. We get the size of the image here as well, the width and the height. And here we also calculate the number of blocks. We create an empty NumPy array with the same dimensions as the image. The array will be used to store the pixel data of the new image. We create the reverse mapping from the values to the keys of the original mapping. This is done because we want to know the new position of each block in the image based on the mapping. Then we iterate over each block in the image, the Y and the X. We calculate the coordinates of the current block in the image. We crop the current block from the image and convert the result to a NumPy array. We calculate the new position of the block in the image based on the reverse mapping. And then we place the block at its new position in the new image data array. Finally, we convert the new image data array back to a PIL image object and save the new image to the output path. So this is the complete script, and this should be able to reverse the shredded image in all 11 different ways that we found. So let's try this out. First, we can try it out on one of our shredded images, just to make sure that it can reverse one of our test data files. So let's see. Let's just rename the loss.png file to flag.png. And then we can copy one of the reversed unique files. Let's run the script. Let's have a look in the reversed folder. And here we see that it has successfully reversed the image. Let's go back to the terminal and try the script out on our flag.png and rename it back. to lost, since that's what's hard-coded in the script. And let's run. And here we have the reversed images. And here we can see that we have found our flag. So Crate-CTF governmental security approval was only a pink and green unicorn dream. And that wraps up this challenge. Thanks for watching. I'll see you next time.